Aloha BioChem 141. In today's lecture, we cover Chapter 1 material, the chemical composition of matter, and chemical changes. Hello again. In today's lecture, we will go through the third way of categorizing matter. Recall in our previous two lectures, we described two ways to divide matter into different categories. The first one, matter is either naturally occurring or it's synthetic. In the second method, matter is divided into solids, liquids, and gases. The third way of categorizing matter is by chemical composition. And this will be the most detailed of the three. But before we get into that, let's first discuss chemical changes. Recall in our previous lecture where we talked about physical changes. Physical changes are when a substance undergoes a transition, but the identity of the substance remains the same. An example would be when solid water melts into liquid water. You still have water after the transition has occurred. But chemical changes, on the other hand, are when you do generate a new type of material. So substances do alter their identity. Chemical changes are also called chemical reactions. So it happens when one material converts into another and changes in substances' identity do take place. We'll discuss a lot more about chemical reactions as the semester progresses, especially in Chapter 5, but we can't go too much further without at least mentioning a few things about them. Here's an example of a simple chemical reaction, the combustion of hydrogen, or the burning of hydrogen. Hydrogen is an explosive gas. In fact, it's used as rocket fuel, and it's very dangerous stuff. And if you light it with a spark, what happens is the hydrogen gas combines with the oxygen gas in the air, and boom, the two convert into water vapor. So you start off with hydrogen gas and oxygen gas, and if you add the spark, then boom, and then all of a sudden you have water vapor. So you generated something new, and therefore this is a chemical reaction. So remember that chemical equations tell you the chemicals that you start with on the left, this is your reactant material, and the chemicals that you end up with on the right, this is your product material. And you can see this time you have different chemicals on the left versus on the right. So here, this is definitely a chemical reaction. The formula for hydrogen gas is H2 gas. So ignore that 2 up front for the moment. If you have a sample of hydrogen gas and you were able to look at the particles of hydrogen gas, you would see that they all look like this. Each particle is 2 hydrogen atoms attached. So there's one particle of hydrogen gas and there's another one. So these are 2 molecules of hydrogen. So that's what that 2 up front is for, is you start with 2 molecules of hydrogen. And when these 2 molecules of hydrogen combine with 1 molecule of oxygen, a molecule of oxygen is 2 oxygen atoms attached together. Then when these molecules all combine and you give it a spark, then boom, what happens is you end up with 2 molecules of water. Now look at the atoms and count how many hydrogen atoms you start with all together and how many hydrogens you end up with. So you have 2 hydrogen atoms in the first molecule and then another 2 here. So that's 4 hydrogen atoms at the beginning, and then you have 4 hydrogen atoms at the end because there are 2 in each water molecule. And then the 2 oxygen atoms that you start with are still there, but they're in separate water molecules. So you see in a chemical reaction, what happens is atoms become detached from one another and they recombine with different atoms. So you end up with different substances. Your author also illustrated this chemical reaction in the textbook. And here it is right here. You can see she drew 4 hydrogen molecules reacting with 2 oxygen molecules and generating 4 water molecules. So she did twice as much reaction as I've drawn right here. One more example of a chemical reaction in the textbook. Here's one right here. Now, the chemicals aren't listed in this picture, but this is oxygen gas, 2 oxygen atoms. So this is an oxygen gas molecule, and you have 4 oxygen molecules. And this right here, this is CH4, 1 carbon atom attached to 4 hydrogen atoms. So this is a methane molecule, and you have 2 molecules of methane. And in the products, you end up with 4 molecules of water, 1, 2, 3, 4, and 2 molecules of carbon dioxide. That's carbon and 2 oxygens. Now, without even knowing what these molecules represent, you should be able to classify this picture as a chemical reaction because you have different particles on the left versus on the right. You see, on the left, the hydrogens are all attached to carbon, but on the right, the hydrogens are now attached to oxygen. So atoms have been detached and recombined in this picture. So without even knowing what these represent, we can classify this as a chemical reaction. This is the combustion of methane. Now it's time to get into the third way to classify matter. However, one more quick thing. Remember when we discussed physical changes and there were corresponding physical properties? Physical properties are properties of a substance that can be observed without changing the identity of a substance. You can look at the color of a substance without it changing its identity, so that's a physical property. You can measure the mass of a substance without it changing its identity, so that's another physical property. And there are many physical properties. Along with chemical changes, we can talk about chemical properties, and to observe a chemical property, you have to have the substance undergo a chemical change. So for example, combustibility. Does the substance burn? That's a chemical property, and it can only be observed by burning the substance. So you have to do a chemical reaction in order to observe a chemical property. So just be aware that in addition to physical properties, there are chemical properties. Now is the time to discuss the third method for categorizing matter. Remember, matter is either natural or synthetic. It's a solid, liquid, or gas. Now the third method is the most detailed, and this is by chemical composition. So to get a grip on this one, it helps to kind of look at this tree diagram right here, and the author has a similar tree diagram, but let's discuss this one. Most of the matter that you'll come across in nature is a mixture of different substances. If you go outside and you scoop up a pile of dirt in your hand, inside that pile of dirt, you'll see lots of different things. You'll see sticks and rocks and pieces of metal. So there's lots of different substances in that one mixture. Another example of a mixture would be salt water. If you go out to the ocean, you just scoop up a little bit of salt water. You'll have some salt in there, some water, probably some organisms, lots of different things in the salt water. So a mixture is when there are 2 or more substances combined in variable proportions. Variable proportions. Okay? Some salt water might be more salty than other salt water. If you get your salt water from the Dead Sea, there's lots of salt in there. If you get your salt water from, a brackish lake, there's less salt in there. So different samples will look different. Okay? Different samples of dirt, depending on where you get them, would have different proportions of the substances in there. Some dirt might be very rocky, and other dirt might not be. So mixtures look different depending on where they come from. So salt water is an example. Air is another example of a mixture. So air, depending on where it comes from, might have some smog in there. It might have some fog in there. If you live here in Hawaii, we have a sulfur dioxide gas coming from the Big Island sometimes, and that dirties up our air. Now, brass is another example of a mixture. Brass is a mixture of two metals, zinc and copper. But sometimes brass has a lot of copper in there, and other brass has a little bit of copper in there. So the proportions can be varied. Your textbook author shows you a couple of illustrations of mixtures. So let me point those out to you. So here's some air right here, which is being breathed in by some divers. Now, air is mostly nitrogen and oxygen. Okay, about 20% oxygen and 80% nitrogen. There's always some other impurities like CO2, argon, etc. But for the most part, air is a mixture of these two gases. Okay? But some divers like to fill their tanks up with a higher percentage of oxygen. So the proportions of oxygen to nitrogen can be varied. Okay? So you can tell this is a mixture, by the way, because you have two types of particles. You have these blue particles, which are the nitrogen ones, and the red particles, which are the oxygen ones. Another example of a mixture is salt water. So here's someone who's retrieving a syringe of sodium chloride solution, saline solution, from some IV bag. Now, if you were able to see the molecules and the particles inside the saline solution, most of it would be water, and that would be the background. So you can see the water molecules back there. But then the salt is also in the water. So you have your sodium and chloride particles, dispersed throughout the water. And depending on where you get your salt water solution, it might have more salt or it might have less salt. And in medical practice, sometimes you want a saltier saline solution, and other times you want a less salty solution. And we'll talk about such cases when we get to solutions in chapter 8. But you can tell that this is a mixture because you got more than one type of particle. You got your water particles back here and your salt particles more clearly colored. So that's a mixture. So one more example of a mixture that your author shows is sugar. When it dissolves in water, you get sugar water. So sugar molecules are kind of, these large, complicated looking molecules. But here, that, pure sugar, all you have is one type of molecule, these large sugar molecules. And then when you, have pure water, you just have those pure water molecules. Okay? So these are two separate pure substances. But when you combine them together, if you pour this spoonful of sugar in that water, then the sugar molecules get distributed in the water, and now you have two different types of molecules. You got your sugar molecules and then your water molecules. But again, it's a mixture, not only because you have two types of particles, but because the proportions can be varied. You can add a lot of sugar to the water, or you can add a little bit of sugar. Okay, variable proportions. All right. Now, most material is a mixture. In fact, you will probably never see a 100% pure single substance. Almost everything out there, even if you have some water and you purify it, there will always be a few molecules of impurity and there are a few impurities in there. It's almost an idealization to talk about a single pure substance. But that's what we do in science. You know, we can't always talk about what what you see. We like to idealize things. So there are pure substances that technically, theoretically, you could get if you were very good at purifying something. So maybe if you have the best water purifier out there, you can make some pure water with no impurities, and then you could talk about a single pure substance. Or maybe if you had some gold in a cave that you discovered, you could get rid of all the impurities and have some pure gold. Okay, so a pure substance is one single substance. It doesn't matter where it comes from, it always looks and behaves the same. So if you have 100% pure water that over here in Hawaii, it's going to look and behave exactly like 100% pure water over there in Zimbabwe. The water in Zimbabwe might be worth more than it is over here in Hawaii, but the samples would look the same and they would feel the same and they would behave the same. They would have the same properties. So different samples look and behave the same. There are lots of pure substances out there, more than anyone could count. So here are just a few examples. Pure oxygen gas. Imagine pure oxygen gas. Okay, pure gold. 24 karat gold with no impurities. That would be quite valuable. Pure glucose sugar. Pure water. Now, pure substances can be divided into two categories. They are either elements or compounds. Elements, I know you've heard of these, and we're not talking about the Greek elements, earth, water, air, and fire. We're talking about the 118 elements that we all have seen in the form of a periodic table, and I'll show you that right here. So there is the periodic table. So what an element is it's a substance which cannot be broken down further by any physical or chemical change that you can think of. So if you have an element, it's a substance, and no matter how much melting or boiling or how much, whatever you do to it, you cannot divide that into two simpler substances. You cannot break it down any further. Okay, that will always, as long as you don't introduce anything new to it, there's nothing that you can do to the element that would separate it into two simpler substances. Whereas salt water can be separated into salt and water because it's a mixture. An element cannot. Okay, a single pure element, there is only one type of atom in the element. So we see a list of 118 elements here. So we'll just list a few examples. Hydrogen is the first one on the list. So you go way up here. There's hydrogen. It's element number 1. Carbon. This one is a little bit further down. It's element number 6 right there. There's carbon. And then nitrogen is right next to carbon. It's element number 7. And then oxygen's element number 8. By the way, these 4 elements are the most important ones in this class. So 96% of the human body is comprised of these 4 elements. So we'll talk quite a bit about them. But there are many other elements on the periodic table. And we'll mention quite a few of them as the semester progresses. But I don't know all of them and all of what they do, but these are the big guns right here. So we'll be talking quite a bit about them. So again, to reiterate, if you have an element, you only have one type of atom. So I'll show you, let's see. Here are a couple of examples of elements in the textbook. Your author has listed right here, aluminum foil. So aluminum foil, this is a solid substance, and aluminum is one of the elements. You can find it on the table. So there it is, right there. It's element number 13, okay, right below boron. So there it is, and the aluminum foil. It's a solid, so all of these aluminum atoms are packed together, cram-packed. It's a rigid structure. You know, I know you can bend the aluminum foil, but you know, that's just the overall, you know, large foil. If you're zooming in on, you know, any submicroscopic area, the atoms are all locked together, okay? So you only see one type of atom in here. Another example of an element is nitrogen gas. So nitrogen gas is made of N2 molecules. So, you know, again, though, you only see nitrogen atoms in here, although two of them combine together to form a single particle of nitrogen. These are all nitrogen particles. Okay, the next two are examples of compounds. So let's talk about compounds now. So if you have a pure substance and it's not an element, then that means it's a compound. Compounds are two or more elements that are combined in fixed proportions. So don't get confused between the definition between mixture and compound. Let's go back and forth for a moment. Mixtures are two or more substances combined in variable proportions. Salt water, you might have a lot of salt and a little bit of water, or a little bit of salt and a lot of water. So two substances or more combined in variable proportions. But a compound is a single substance which is made of two or more elements combined in fixed proportions. So since you have two or more elements, that means you have two or more types of atoms in there. And compounds, unlike elements, can still be broken down into their constituent elements. Examples of compounds are water, salt, and glucose. Now each compound has its own chemical formula. Water, the formula is H2O, so we can see that water is made of the elements hydrogen and oxygen. And we can break water down into its elements hydrogen and oxygen if we wanted to. But this is a single pure substance, okay? The elements hydrogen and oxygen are always combined together in fixed proportions. It's not like some water has more hydrogen than other water. No. If you're talking about pure water, the proportions of hydrogen to oxygen are always fixed. There's always 2 atoms of hydrogen for every 1 atom of oxygen. Okay? The proportions are always fixed. Salt, the proportion of sodium to chlorine atoms in salt is 1:1. For every sodium, you have 1 chlorine. And glucose, there are 3 elements that make up glucose: carbon, hydrogen, and oxygen. Every molecule of glucose, it's a bigger molecule. Every molecule, if you were able to see inside of it, has 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms for every single molecule of glucose. Now, compounds, like we said, can still be broken down into their elements. Elements cannot be broken down any further. So we will talk more about elements and compounds in later chapters. But before we end this lecture, we've been through kind of a lot, and I think we can get a better grip on these terms: mixtures and elements and compounds, and variable proportions and fixed proportions. That's a lot of stuff there. I think we can get a better handle on it if we go through a simple exercise, which I like to think of as the goal of alchemy. So here we go. This is an exercise in purifying matter. Now, this is the goal of alchemists. And if you have heard of alchemists or alchemy, but you don't quite know what it is or who they were a group of people that were on a mission to purify matter. Okay? They had some impure metal. They wanted to purify it into more pure metal, gold, for example. And if they had a mixture of different substances, their goal was to purify that mixture and separate it into its constituent substances. So they were experts at separation techniques, and this was basically their purpose in life. And they would run experiments over and over and over again to become more adept at these separation techniques. So if you give an alchemist 120 grams of salt water, it would be his duty to separate it in as far as he could. Okay, and the first method of separation would be to divide the salt and the water, and the way he could accomplish that is by distillation. So if you take salt water and you distill it, you can separate out the salt from the water. So I'll show you a quick video of distillation right here.
With an experiment, take some salt water in a retort and heat the retort till the steam comes out of it. We will see the steam getting collected inside the beaker in the form of droplets of water. The steam condenses and reaches the beaker, and the salt left behind in the retort. This method of separation of soluble solids from liquids is called with an experiment.
Okay, so you see it? You have your salt water, and basically you're boiling off the water and leaving the salt behind. But the steam that you boil off, it goes through a cold tube and it recondenses to form the liquid over here. So you separate the salt from the water. And alchemists were experts at this technique. They knew distillation. But it's important to realize that distillation, during that process of distillation, there were no chemical changes that took place. The water in the retort started as liquid water, and once it boiled off, you had steam, which is gaseous water. And then funneling that water down the cold tube, it recondensed back into the liquid phase. But the water remained water throughout the entire process. Likewise, the salt that you started with was an aqueous solution, but as soon as the water left, you were left with solid salt, but it's still salt. So you can see the chemical equations here describing the process of distillation. What happens to the water? You have two chemical equations, this one and then this one, and then the salt, there's one chemical equation. So it turns out in this mixture of 120 grams salt water, there were 20 grams of salt and 100 grams of water. So the alchemist didn't know that until after the experiment. So 20 grams of salt and 100 grams of water. Now these two substances are examples of compounds. Compounds are when you have two or more elements combined in fixed proportions. Salt is a combination of the elements sodium and chlorine, and the proportions are 39% is sodium and 61% is chlorine by mass. And water is a combination of the elements hydrogen and oxygen. 11% of water's mass is hydrogen and 89% of water's mass is oxygen. That might be a little unsettling because after all, 11 to 89, I thought there were twice as many atoms of hydrogen versus oxygen. Well, that's true. There are always twice as many hydrogen atoms as oxygen, but the hydrogen atoms are very light. They weigh 1/16 of an oxygen atom. So even though you got twice as many hydrogen atoms, the mass of any sample of water, 11% of that mass is comes from the hydrogen atoms, and 89% of it comes from the oxygen atoms. Okay, so here's a water molecule. That oxygen atom is much bigger than the hydrogen atoms. Okay, so now you have these pure substances. They're both compounds because they're made of two or more elements combined in fixed proportions. If we separate these compounds into their constituent elements, or if the alchemist is able to, then it's going to undergo a chemical change, because you start with a substance and you end up with different substances. Now, alchemists way back didn't know how to do this separation. They thought water was a single pure substance. It wasn't until like the 1700s that someone was able to do this. So, you know, the process of separating water into its constituent elements today is pretty easy, and we can accomplish this through electrolysis. So let's take another look at a video of electrolysis. Okay.
Let's see the results of our experiment. Take my battery and I'm going to place it right in the water, and immediately you're going to start to see something happening.
All right, you see that? All you have to do to separate water into its constituent elements is to electrocute it. You take a simple battery and you immerse it in the water, and at one terminal you see a few bubbles coming off. Those are the oxygen gas bubbles, and at the other terminal you see a lot more bubbles coming off, and that's the hydrogen gas bubbles. So there you go. The water is being separated into hydrogen and oxygen. So pretty cool. Now, if you have 100 grams of water and you divide it into its constituent elements, you will always end up with 11 grams of hydrogen and 89 grams of oxygen. The proportions are always fixed. 100 grams of water, no matter where the water comes from, yields 11 grams hydrogen, 89 grams oxygen. It's an 11 to 89% ratio by mass, or a 2-to-1 ratio by atom count. Salt can be divided into its constituent elements through a similar electrolysis process. You would need to melt the salt, though, to have molten sodium chloride, and probably a stronger battery, but you could still do this. And you could take your NaCl and convert it to sodium and chlorine, the separate elements. And if you have 20 grams of salt, since salt is always in fixed proportions of 39% of the mass is sodium and 61% of the mass is chlorine, so 20 grams of salt would yield 7.8 grams of sodium metal and then 12.2 grams of chlorine gas. Okay? No matter where the salt comes from, if you have 20 grams of it, that's how it divides up. So you can see these compounds can be broken down into the elements, and these occur through chemical changes. So the chemical reaction for the electrolysis of water, you start with the water, and then you end up with the hydrogen and oxygen substances. And for sodium chloride salt, you start with the salt, and then you end up with sodium metal and chlorine gas. So pretty cool. And I hope that this exercise right here helped you understand the difference between mixtures and compounds. Sometimes that's a source of confusion. Anyway, that kind of sums up our discussion on the matter portion of this chapter. In our next lecture, we will go into measurement. So stay tuned for that. Aloha.